Hi, my name is Yaling from the University of Arkansas. I am here representing my colleagues David Darling and Qinghua Li to present our work, Privacy Protection Against Shoulder Surfing in Mobile Environments. Consider this scenario. You're sending a message on your phone, but there are people standing closely behind you. It is very easy for them to read your conversations or any other sensitive information on the screen, and obviously this is a problem. And ideally, this is what we want. You as the user can still use your phone to read your messages, but the eavesdroppers cannot recognize any content displayed on the screen. The first solution coming to our minds is a privacy screen filter. You can see the screen when you are within a certain amount of viewing angles, and it gets considerably darker beyond this angle range. However, screen filters have a number of limitations. For example, they do not block people staring from behind you, as long as these people are also within this allowed angle range. And therefore, instead of resorting to hardware mitigation tools, we are looking for solutions that are software-based. This is not a new idea. Many previous works attempted to provide shoulder surfing protection schemes. However, they all have their own weaknesses. Some work focus only on specific attack vectors. A common example is passwords. But our work provides protection on all types of sensitive data that could appear on the screen. Some works provide proper protection on sensitive content by obscuring certain parts of the screen, but their obscuring techniques could make it difficult for the users themselves to use the phone. In comparison, we offer a more flexible solution for users so that they can customize the level of blurriness by their own preference. Many works focus on the fields of protection on non-mobile platforms, but our main target is mobile environments. There are also works that focus on alerting users when eavesdroppers are detected around them. In comparison, our detection and obfuscation scheme is activated by the users, and we aim at a different aspect, which is to make the sensitive content recognizable to users but masked from the people nearby. And lastly, there are a couple works that risk exposing users' information when only critical chosen area of the screen is shown. Now I'm going to present our work. It has three major contributions. First, user interface is an image, and private object detection detects sensitive content displayed on the screen. And we also design dynamic sample generation and model retraining to allow users to customize the model. And lastly, we create a lightweight solution specifically for web applications, mainly due to the popularity of web applications. Now I will introduce the design of our first model, user interface as an image. This is the pipeline. It starts when a user turns on the mode to switch to user interface as an image mode, and immediately an UI view of the screen is pre-rendered. Next, content detection algorithm runs on the UI view. If any sensitive content is detected, the Gaussian blurring technique is applied on the sections that contain sensitive data, and then the processed view is displayed to the user. Now the user can switch back to the normal mode whenever they want to. Three contributions make user interface as an image valuable. First one is that it does not require complex UI logic for dynamic hiding of the content. So content displayed on the mobile screen is actually distributed among different layers, and our model makes it possible to ignore the complicated details when processing the screen content. Second, our technology can be applied by app developers easily. And third, there are bountiful technologies to apply on pre-rendered images. Due to the time limit, please read the paper for more information on the second and third points. I'm going to go into more detail on content detection in our user interface as an image design. Our content detection employs YOLO v5, which is one of the latest object detection models developed by Ultralytics. It is known for its high inference rate and small model size, which make it ideal for mobile devices. And the benefits that I've just mentioned, they are embedded in its design and architecture, especially the design of the backbone and the PA net. And I will leave out details of the YOLO v5 architecture due to our limited time. For more information, please refer to the paper on YOLO v5. These are the results of the content detection model. The input dataset consists of message app screenshots, and the output images have squares around detected sensitive data. Each square also is tagged by a category and a confidence interval. During the training process, the model had an input dataset of 188 examples, and it was able to achieve a precision of 98.17% after 450 epochs. The training process took about 14 minutes. To test one image, it took about 10 milliseconds, and the evaluation process was carried out on a NVIDIA Tesla T4 GPU chip. As I have mentioned earlier, the second major contribution to our work is to allow users to show the program what type of data is sensitive to them, since it is not possible for the model to anticipate all scenarios where sensitive data could appear. And we did this by introducing dynamic sample generation and model retraining. So now the user can manually identify a UI element that they wish to hide within an app, and many training examples of the same element will be automatically generated using visual transformation. And on this slide, these are the main transformation techniques that were applied to the training examples. This figure shows some of the output of random transformation and augmentation applied over a subset of the text message dataset. During evaluation, 10 images of the text message dataset were used to generate 150 augmented images, which are then fed into the same YOLO v5 model we used earlier, and we were able to get a precision of 95.65%. After sensitive content is detected, the next step is to apply a blurring filter to hide the sensitive data from attackers. Out of all the available blurring filters, we chose the Gaussian blurring filter because it allows low frequency content of images to pass through, and it creates a smoother, blurrier effect on the object edges. This is an example of applying a Gaussian blurring filter on a text message image. The image on the far left is the original version without any processing. From the second to the fourth images, different levels of blurriness are applied to the original image, and we believe that these options give users more flexibility as to what level of blurriness they prefer. Now I will talk about our private content protection scheme specifically designed for web applications. This project is part of our agenda because web applications are so common and frequently used on mobile devices, and they're especially vulnerable to shoulder surfing attacks because there could be all kinds of sensitive data appear on websites unexpectedly. And additionally, the Chrome extension that we offer as a solution is a very lightweight tool. As we will see in the performance evaluation, it does not consume a noticeable amount of resources. Our solution for web applications is a Chrome extension. Our extension can be loaded in all Chromium-based browsers, including Safari on iOS and Kiwi browsers on Android. And in fact, in 2021, among the top 5 top browsers making up the largest market shares worldwide, all the Firefox were Chromium-based. So we believe that our Chrome extension can be used in a wide range of scenarios. And on this slide, you can see the workflow of the extension. Upon page loading, a content script is triggered to run, and our algorithm tries to detect if there exists any sensitive data. If there is, obfuscation technique is applied to the web page. First, we define the major types of sensitive data that our extension should protect. Credentials are obviously a must to include in the list, and there should also be other data such as standalone email address input fields, and also credit card information, and so on. To convert the defined sensitive data so that we can program them in the algorithm, there is a list of HTML elements that deserve special attention. So there are form elements that are sent by post methods, input fields with email or telephone as their attributes, iframes, because it is common for iframes to contain bank transaction data, and lastly, login or sign-up buttons, because they can dynamically create new sensitive data on the page. There were 2 major challenges that we had to overcome. The first one is to deal with the asynchronous data communication nature between browsers and servers. We tried first to implement a method called window.request animation frame in order to solve this issue, but we failed because it caused a severe deterioration in performance. Then we tried to invoke set timeout and with 1 second or 3 seconds or 5 seconds as the argument options, so that the detection algorithm runs 1 second and then 3 seconds and then 5 seconds after the page is first loaded. So we do this to make sure that all data are rendered on the web page when the detection algorithm runs, and this solution turned out to work for most case scenarios during testing. The second challenge lies in the login and sign up buttons. We handled it by attaching an event listener to all detected login buttons or sign up buttons that exist on this page, so that when the button is clicked, the detection algorithm is run again on the updated page. If the algorithm indicates that sensitive data is present on the current web page, we would first check if the data is contained in a form that is decorated by a post method. If so, the form is rendered blurry. And then we check if there is a standalone email input field, and if there is one, we make it blurry. We added the email input field to this algorithm because it turned out that a lot of websites such as Amazon or Walmart.com tend to have an email address field for user subscription. And lastly, if the sensitive data falls into any other categories, according to the web pages that we have tested, it is appropriate to make the whole page blurry, as the sensitive data in this case occupies the whole page. And these are some of the Chrome extension output images. The 5 examples are tested on iOS systems or Android systems. The first 2 web pages contain credential input fields and they are rendered blurry. The third and second examples have patient information wrapped up in a form and the form is blurry. The last screenshot has a single email input field for subscription and only that field is rendered blurry. Our Chrome extension was tested on 96 web pages with the highest traffic during that time period, and there were in total 483 pages visited. The false negatives take up about 5.0% of all visited pages, and the main reason causing it is that the list of keywords that we use to capture sign-up buttons or login buttons was incomprehensive. For example, one web page has a sign-up button called Join Us Today, which we did not anticipate. There were 18 false positives, which was about 3.7% of all web pages. And the primary cause for the false positives is that some HTML elements that do not appear to contain sensitive data from they're actually wrapped up in a post method forms. Yeah, and a good example is the Add to Cart button on Amazon. To sum up this presentation, we have designed an automated private content protection scheme for generic applications and achieves 98.17% mean average precision at 0.5 intersection over union. And our works also contains a dynamic sample generation and model retraining model. And lastly, we developed a Chrome extension for private content protection in web applications. Thank you for your time, and now we're ready to take questions.